So I shall share my screen now. So welcome all of you in the fifth tutorial session of Power Electronics Applications in Power Systems. So just to give a brief about last week's discussion. Last week we solved some numerical problems on the uh, midpoint midpoint voltage compensation. So when during light load condition, the voltage of the midpoint rises above the rated voltage. So that is an over voltage, and during rated towards the rated condition, when the load is high, there is an under voltage. To mitigate that, we needed reactive power compensation. So we solved different numericals on those topics. Today, last day we saw like why reactive compensation is required, and today we shall discuss how what is the way to do that reactive power compensation. We already discussed that we need some inductive reactance or some capacitive reactance based on whether we require to absorb the reactive power or we require to provide reactive power. When it when it is required to absorb the reactive power during light load condition, we need reactive inductive reactance like which is basically inductor, and during when there is an under voltage and we require to provide reactive power, then we need capacitive reactance, right? So we need a capacitor bank or something like this. Today we shall see in detail that what is done to do that reactive power compensation, what we do usually. Okay, so first of all, I hope that you have already watched the videos. I shall just briefly discuss the theoretical part. So this picture over here, this is called Thyristor Controlled Reactor. Okay, TCR in short. What is this? There is this bus. So here, suppose this has some voltage, 400 kV or something, and then there are these devices connected in this fashion, and then there is this inductor, right? So this is the single line diagram. So do you know what this device is called? Do you know what we call this and this?
Thyristor bidirectional.
Yeah, this is thyristor, but there are many device. These are basically semiconductor devices, right? This is where the subject name is applications of power electronics in power systems. This is where the power electronics comes, right? These are semiconductor devices, and one of the semiconductor devices, a group of semiconductor devices is called basically thyristor, and this particular type of device we also sometimes called silicon controlled rectifier, SCR. Okay,
SC.
silicon controlled rectifier. What is this? So I don't know. I do you have some basic idea about SCR or thyristor, how this works? Have you read anywhere?
Um,
Sorry.
only name or listen, madam.
Okay, so you don't know how this works. Uh, okay, so I shall try to briefly just tell you about this.
Yes, ma'am.
Okay, so it so this has basically three terminals. This terminal is called cathode, this one. This terminal is called anode, and this terminal is called gate terminal. I hope you have already heard about diodes. Now, this switch has similarity with diode, but it is slightly different than diode. So, diode has two terminals basically, cathode and anode, right?
Yes, ma'am.
Cathode and anode. And when does a diode conduct? When it is forward biased. When
Forward.
the anode potential is positive with respect to the cathode potential, then the diode will conduct in this direction. For
Yes.
thyristor also, there is anode terminal, there is cathode terminal, and the current flows from anode towards cathode. But there is a catch, and the catch is this third terminal, which is the gate terminal. For
Okay.
thyristor, when the thyristor is forward biased, that is when anode potential is greater than the cathode potential, the thyristor is now ready to conduct, but it will not conduct until you provide a trigger signal. Okay, so this is kind of a green signal. It is ready to conduct when it is in when it is forward biased, but the moment you get the gate signal, then it will start conducting. So there are basically two conditions for a thyristor to conduct. The first condition is that it should be forward biased. So V anode should be greater than V cathode. That is the first condition. That
Okay.
is the first condition. And the second condition would be that the current flowing through the thyristor should be greater than the latching current. There is a current called latching current. If the I is greater than IL, then it will be latched to the on state. Then it will remain in the on state. Okay. So these are the condition. And when if the thyristor is reverse biased, in that case it will not conduct. Okay. It will not conduct if it is reverse biased. So these are another term, like you can read it in detail. There are like, this is a very common device, so you can read it anywhere in the internet, or you can consult some standard power electronics books. So there is another term that is called the holding current. So this is during turn on. During turn off, first of all, if the device is reverse biased and the current is lesser than holding current, then it will turn off. Okay, the current has to be lesser than holding current, right? If the device is forward biased and the current is greater than holding current, then it will not be off, right? So these are some of the requirements for the thyristor to turn on and turn off. Now you can see this is also called a semi-controlled device. Okay, why? Because we can control the turn on time, but like instant, but we can't control the turn off. The turn off is decided by the circuit condition, but the turn on we can control by deciding to when to give this gate signal. Okay, whenever we will give the gate signal, it will turn on. Otherwise, it is in a position to conduct, but it is, if it is not triggered, then it will not conduct. Okay, so that's why it is called a half controlled or semi-controlled semiconductor device. Okay. Now you can see, as it conducts current in only one direction. That's why we have this kind of configuration. So for AC current, it will obviously, it is alternating in nature, so it will change its direction. When the current is flowing in this direction, this SW1 will conduct, and when the current is flowing in this direction, then SW2 will conduct. Okay. That's why this configuration is required for AC current. And then obviously we require an inductor because we need reactive power compensation. So definitely an inductor is required. Okay, fine. Now, basically, here some assumptions are taken. What is the assumption? That there is no loss in these devices. Practically, there are loss in these devices. no device is lossless, but for the ease of analysis, for now we will consider that these devices are lossless, SW1 and SW2. Now if you just apply KVL here, then this is the KVL equation. This is Vt, the bus voltage, minus L di by dt equal to 0. So Vt becomes L di by dt. So I think you one of your mic is on. Can you just please shut it off? Yeah, thank you. So this is the voltage, right? And what is Vt? Vt is a sinusoidal voltage Vm sin omega t, where Vm is the peak value, right? And omega is the power frequency. So for us it is 50 hertz, 2 pi times 50, right? So this is the angular frequency. Omega is 2 pi 50. Okay. Now, one of the questions arise here that we need reactive power compensation during light load condition. There is an over voltage. So if we just put an inductor here, then the inductor will absorb the reactive power and the voltage we can maintain at a certain point. Now the question is why these devices are required. What will they do? Inductor is definitely required, but we could have simply put an inductor. What is the requirement of these devices? As I just told you that you can control the turn on of these devices, right? You can dictate when you want these devices to conduct. And if these devices are turned off, then the current can't flow through the inductor, right? So based on this, you can just you can have a variable, you can offer a variable reactance over here. Okay. Because so if you are able to control the turn on instant, then you can also able to control the duration till when the current will flow. Okay. So you can dictate the duration of conduction. That's how you will be able to provide a variable susceptance or variable reactance, whatever, to this voltage, and then the current value will change. That if the current value changes, then the reactive power also changes. So as we require a variable reactive power based on the load condition, that's why these semiconductor devices are used. Okay. Till this point, did you understand what I told? Okay. So now, what we will do now, we will derive the current expression. What is the current? So voltage was L di by dt. So for deriving the current, we need to integrate the voltage across the inductor. So we have integrated this 1 by L integral Vt times Vt dt, and the expression we get is this minus 1 by omega L Vm cos omega t plus c, where c is the integration constant. Here comes a new term, which is alpha. What is alpha? This alpha is called the firing angle, right? This alpha is called the firing angle. What is firing angle? I will just explain it with a diagram. That way it will be easier. Suppose this is the voltage Vm sin omega t. This one is the voltage waveform, right? This one is the voltage waveform. Now, if these thyristors are not there, there is just this voltage and there is an inductor. You know that this is basic electrical engineering, that the current will lag the voltage by 90 degree because this is a pure inductor. So the current will lag the voltage by exactly by 90 degree, right? Now, when these devices appear, then you can you can turn on them in a way so that they will not conduct throughout the time period. They will conduct for certain period of time, not in the whole time period. Okay. So they will conduct only for this portion, and then in these portions the current will not flow. Why? Because the thyristors are off now, right? So this angle is what, starting from this point, after which angle the conduction starts. This is called the firing angle. This is also called the delay angle sometimes. So after which angle the current starts flowing with respect to the voltage zero crossing. So this is where the voltage starts, and this is where the current starts. This angle is called alpha. That is the firing angle. And you can vary this alpha. You may also prefer to start the current here. You can also prefer the current to start. You can, so alpha you can vary. Okay, you can vary the alpha, and based on that your current, the conduction, the duration of conduction will change, and current value will also change. Okay, so when right, so when your current is zero, at that time we can have this equation. When omega t equal to alpha, at that point, at that instant, current is zero, right? Because that's when the current starts, that's when the conduction starts. So from there we can find out what is the constant C, which is this, and then what is the current. The current expression is this: Vm by omega L cos omega t minus cos alpha. And this is valid for any firing angle, any current. Okay, it may be the full conduction, it may be partial conduction, but this equation is valid for all of them, right? Another angle is defined, that is sigma. This is called the conduction angle. The conduction angle is what? The duration when the conduction happens, when current is flowing. So this duration is called sigma, the conduction angle. These two angles are actually very important. Okay, right. Okay, now one thing over here is that when when the current is continuous like this, then there is no problem. This is, if the voltage is sinusoidal, the current will also be sinusoidal with some lag, right? Lagging by 90 degree for a pure inductor. But when the current is discontinuous like this, sometimes it is zero, sometimes it is there. In that case, some harmonics will be introduced. You can understand that there will definitely be some harmonics. What are the harmonics? Harmonics are the component of the current apart from the fundamental. So there will be a fundamental whose frequency will be omega t, right? That is the frequency of the voltage. And there will be multiples of this omega t, right? So 3 omega t, 5 omega t, all these things will be there. 3 omega t, 5 omega t. These are called the harmonics. They are obviously unwanted because they are, they are not useful. So they don't, basically, they are not, they don't give us useful power. If you just multiply this frequency component with the voltage, you will not get any average power, right? Because the frequencies are different. You will only get useful power when the frequency of voltage and the frequency of current are same. Otherwise, these are of no use. That's why they are not good for the circuit. They are filtered out. Okay, so there are some filter circuits are used like this in parallel. There will be some LC filter. Okay, some LC filter will be there to filter out this harmonics. Okay, like this. So what will they do? They will offer a lower impedance compared to this to the higher order harmonics, and the higher order harmonics will flow through like this through the filter, and the harmonics will not uh, follow this path. They will instead follow this path. Okay. Yeah, so we can using Fourier series we can find out what will be the value of the fundamental. So there is, as I already told, there will be a fundamental embedded within this. So there will be a fundamental that is embedded within this, that is embedded like this, and then there will be some harmonics. Okay. So what is that fundamental? That fundamental is this. This you can find out by using Fourier series, and the harmonics will be this. Okay. What type of harmonic we get? We don't get even harmonics. Okay. Why? Because here you can see the current is symmetric. So the even harmonics are cancelled. You can also find that out from Fourier series. Only the odd harmonics will be there. So like this 2k plus 1 where k is 1, 2, 3, all these numbers. So you get third harmonic, fifth harmonic like this, third, fifth, seventh, ninth, 11th like this. Okay. These are the harmonics. And here there is one graph. So alpha is basically varies from pi by 2 to pi. When alpha is pi by 2, you get the total current. And when alpha becomes pi, then the switches are completely off and you don't get any current at all. Okay. So from where alpha is measured from this point, when the zero crossing of the voltage is there, from this point onwards we measure alpha. So the alpha starts from pi by 2, that is the minimum value, and it could be till pi. Okay. So this is the range of alpha, pi by 2 to pi. Okay. So now I shall start the numericals. Before that, if you have any question, you can ask. Another thing I would like to point out that here it is written bidirectional switch, but bidirectional switch, we are defining this whole thing, okay, not one individual switch. This whole thing is bidirectional switch because if you consider this whole thing as a single entity, then you can see we can the current can flow in this direction as well as in this direction. That's why this whole thing is called a bidirectional switch. But individual thyristors can carry current only in one direction, not in both the directions. Okay, so first question. Which of the following order harmonics is or are negative sequence harmonics? Okay. We just now we discussed that if the conduction is partial conduction, that means the current is discontinuous, it is not flowing continuously, then some harmonics are introduced in the current. And usually we get odd harmonics. We don't get even harmonics, we get odd harmonics because the currents are symmetric. Okay. There will be half wave symmetry, all these things. So odd harmonics we get. Among them, which are positive sequence, there are some positive sequence harmonics and some negative sequence harmonics. So are you aware of the concepts of positive sequence and negative sequence? Have you heard of it in power systems or anywhere? Okay, so I guess you are not aware. Now, in power systems, we define the phase sequence usually like this. This is suppose A, and this is the reference one. And this is B, and this is C. Okay. So suppose we like, and counterclockwise angle is positive. So A is 120-degree lagging from B and C is 120-degree leading from A. So the phase sequence would be A, B, C. Okay, this is the phase sequence. Now, if the phase sequence is reversed, A, C, B, like this is the negative sequence. Okay, this is the negative sequence. So how we define them? Suppose if VA, A phase voltage, if we define as, this is for a three-phase system, right? So Vm sine omega t. Sine omega t, this is if this is the A phase voltage, then VB. VB would be, the peak value is same, but it will lag the A phase voltage by 120 degree. So this will be sine omega t minus 120 degree. Omega t minus 120 degree. Okay. 120 degree. And then there will be VC, which will lead A phase by 120 degree. Or you can also write it as sine omega t minus 240 degree. That is same as sine omega t plus 120 degree, right? You can write any of the way. Omega t minus 240 degree. This is the positive sequence. Now for each harmonic, if you just calculate that angle, you will get to see some of them are positive sequence, some of them are negative sequence. For example, fifth harmonic, if you consider fifth harmonic, in that case, it will be sine 5 omega t, right? It will be sine 5 omega t because it is the fifth harmonic. And then for VB, what will be 120 degree times 120 degree into 5 multiplied by 5. That gives us 600. Okay, so this is 600. This is minus 600. Hmm. So now it will be 5 omega t minus 360 minus 240. Okay. minus 240. Ultimately, what you will get? Ultimately, you will get 5 omega t minus 240 degree, because 360 degree, then it will be periodic, one full cycle. So see, for B phase, the fundamental one is omega t minus 120 degree, but for fifth harmonic, it is 5 omega t minus 240 degree. So in that case, the phase sequence changes. Okay, it is the B and C, they are phase angles are interchanged. The B phase one becomes minus 240 degree and the C phase becomes minus 120 degree. If you will calculate, you will see. So that's why fifth harmonic is a negative sequence harmonic. Okay. There is seventh, then third, then 11th. Okay. We can calculate for each one of them. You will see, if you calculate for each one of them, you will see fifth and 11th. These two are negative sequence harmonics. Okay. Generally, how we can represent them? We can represent them like this: 6m minus 1, where m is the order. Okay. M could be 1, 2, 3, anything. So if you just do 6 into 1 minus 5, you will get 5. So fifth order harmonic is the first negative sequence harmonics. Then if you put 2 over here, then you will get 11. So the negative sequence harmonics will be represented by 6m minus 1. What is the next question? Okay, so this is not, this is positive. This would be positive. Okay. What are the positive sequence harmonics? Positive sequence harmonics, right? Now, fifth and 11th, they are negative sequence harmonics, so we can delete them. The remaining are seventh and third. Now, if you consider third harmonic, you will see that VA will be simply Vm sine 3 omega t, Vm sine 3 omega t. And if you consider VB, then it will be Vm sine 3 omega t minus 360 degree. You are multiplying by 3. So this is for fundamental, it was minus 120 degree. For third harmonic, it will be minus 360. Okay. So it simply becomes again Vm sine 3 omega t. Okay. And for VC, it will be 240 times 3, that is minus 720, which is a multiple of 360. This you will also get Vm sine 3 omega t. Okay, sine 3 omega t. So you see there is a special case for so these are called triplet harmonics. The third harmonic, the sixth harmonic, the ninth harmonic, they are always in phase. The three A, B, C, they are in phase. There is no phase difference between them for the triplet harmonics. Okay, there is no phase difference. Okay, so only remaining one is the seventh harmonic. You can also calculate and see that seventh harmonic will be a positive sequence harmonic, because there the phase sequence is same as the fundamental phase sequence. Okay, and the general form will be 6m plus 1. 6m plus 1. So seventh harmonic, then 13th harmonic, they are the positive sequence harmonics. Okay, and so on. So let's go to the next question. What is the purpose of using filter in a TCR unit? That we already discussed. That while while the thyristors are conducting partially, they are not conducting throughout the cycle. In that case, the current is non-sinusoidal. It has a fundamental component along with some harmonics. So, and we want to filter those harmonics. We want to get rid of these harmonics. That's why the filter circuit is used. Okay. So triplet harmonic, sorry, triplet harmonics are in phase, right? What we usually filter out is the lower order dominant harmonics. Means the fifth harmonic, right? The fifth harmonic, the seventh harmonic, the 11th harmonic. These harmonics we try to filter out, okay, by the filter circuit. Next question. Why the TCR units are usually delta connected? So this is another trick. Basically, for three-phase system, if we just go back to the original diagram, yeah, this one, this is a TCR unit, but this is the representation of a single TCR unit, single phase one. Okay. Now for three-phase system, there will be three of them. For each phase, there will be one. Okay. So so for each phase, there will be one TCR unit like this, and they are delta connected. They are delta connected like this. And from here, the terminals are out like this. Okay, so this is TCR1, this is 2, this is 3, suppose. They are delta connected. Okay. Why they are delta connected? Why they are not star connected? Because just now I told you that for triplet harmonics, the third harmonic, the sixth harmonic, which are basically the multiples of 3, they are for these harmonics, the three phases are in the same direction. The three phases are in phase. Okay. A, B, C, they are in phase. There is no phase difference. Now, due to this, we need to restrict them. Okay, we need to restrict them. They shouldn't go out in the line here. They shouldn't go out. So what is the remedy? The remedy is if we just connect them in delta structure, then the currents will circulate in this loop. The currents will circulate in this loop. They will not go out. Okay, that's why the TCR units are delta connected, to prevent third harmonic to flow in the line. Okay. Among the all the triplet harmonics, the third harmonic is the strongest. Why? As the harmonic order increases, the amplitude of them reduces. Okay, the amplitude reduces. That's why the third harmonic is the strongest one. Okay. So the main protection needs to be done against the prevention needs to be done for third harmonic. Question number 5. Why the TCR is paired with a capacitor bank? So earlier we saw that earlier we saw that we were using the SCR with an inductor. right? With an inductor. Yes. Now this inductor, the inductor can absorb the reactive power, right? So this is useful in light load condition when when the reactive power needs to be absorbed. But there are some cases at rated load condition or when the load is near rated, then there is under voltage. In that case, last class we also saw in that case that the reactive power will be positive, right? That means the reactive power compensator should provide uh, reactive power to the line. It should generate reactive power, it shouldn't absorb. In that case, inductor is not useful. In that case, we will need capacitor. So that's why TCR is paired with the capacitor to shift the maximum production limit of TCR to a non-zero value. Okay, non-zero value. Okay, so till this point, okay, right? Okay. Okay, so now I shall take a 10-minute break. After that, I will continue with the rest of the problems. We shall start the sixth question. Consider the following statements about the TCR unit. The TCR unit provides required reactive power compensation by varying the firing angle. Uh, that is the first statement. The second statement is the variation of firing angle results in variable susceptance and thereby changes the fundamental current that flows through the TCR. So, what do you think? Among which option will be correct one? Hello, are you there? Among these two statements, there are these options. Okay, both the statements are correct, and B is the proper explanation of A. Both the statements are correct, but B is not the proper explanation of A. Option A is correct, but option B is wrong. And lastly, option B is correct, but option A is wrong. Okay. So which one is the correct option? Tell which one is the correct option. Option here actually, so the first one is TCR unit provides required reactive power compensation by varying the firing angle. This is true, obviously. That's what we discussed, that as the firing angle changes, the conduction time changes, the current also changes. That's how the reactive power also changes. This is correct. The second, variation of firing angle results in variable susceptance and thereby changes the fundamental current that flows through the TCR. Okay. So this is also correct. Option A is the correct one. So both the statements are correct and B is the proper explanation of A. The next question, consider the two statements. In a three-phase TCR unit, this is the first one, first statement. In a three-phase TCR unit, the reactor is split in two equal halves in each limb. The second statement is, this is done to prevent the flow of dominant harmonic currents. So for three-phase system, we saw that it is delta connected. We also saw what is the reason to connect the TCR units in delta, right? To prevent the third harmonic current flow into the line. Now, if you see each limb of the delta connection, the reactors are connected like this. This will be the reactor. In between, there will be the thyristors. The thyristors will be connected like this. And here it is in opposite direction. Like this. And then again, the reactor like this. This is one limb. Like this, there will be two other limbs of the delta connection. This is L by 2 and this is L by 2. What is the reason? The reason is uh, here they have given this is done to prevent the flow of dominant harmonic currents. This is not true. This is done. The inductor is divided equally so that the whole AC voltage doesn't appear across this thyristors. Okay, the total AC voltage does not appear across the devices. That's why this thing is done. So option A is correct. Option A is correct, but option B is not correct. The next question. Consider the two following statements. Increasing the firing angle of the thyristor beyond 90 degree produces only odd harmonics. In a TCR unit, the thyristors are fired symmetrically in the positive and negative half cycles. So this is true. Increasing the firing angle of the thyristor beyond 90 degree produces only odd harmonics. That is true. And why that is so? Because the thyristors are fired symmetrically. So is this the correct explanation of or not? So this is the correct explanation because the thyristor, uh, the currents that the thyristor in this leg and this leg. So the thyristor in this leg and this leg, their conduction angles are same. Their conduction angles are same. So the currents are symmetric, even though they are discontinuous. Even though the currents may be discontinuous, but they are uh, symmetric over one half cycle. Okay. So the duration here and the duration here, this is there that will be same. Okay. So only the odd harmonics are produced, even harmonics are cancelled. That's why both the statements are correct and B is the proper explanation of A. Okay. Now there is a numerical problem. A TCR unit is connected at the midpoint of a 400 kV, 900 kilometer, 50 Hz long symmetrical transmission line through a step-down transformer of 400 by 11 kV to hold the midpoint voltage at 1 per unit. The reactance is 10 ohm at power frequency. The firing angle is 135 degree. Determine the peak value of the voltage appearing across the TCR unit. Okay, so many informations are given, but this question is very easy. What they are doing, they are giving the rated voltage, the length and the frequency. Then there is a step down transformer. There is an additional component. So this is if this is the bus, then earlier the thyristors were directly connected with this bus, but now there is this will be one step down transformer. Okay, there is one transformer, and then with this transformer, this thyristors are connected. Okay, like this. Here the thyristors are connected. Okay, so I am just showing by switch like this, but they are actually thyristors. And then there will be the inductor. Okay, so the what is this that's what they have given. The step down transformer is 400 by 11. This is stepping the voltage down to 11 kV. Then what is the peak voltage that appears across the TCR unit? Now if suppose this 11 kV, this is the line to line voltage. Okay, this is the line to line voltage. First of all, you will have to find the phase voltage, phase to neutral voltage, that is 11 by root 3. Okay, 11 by root 3. So 6.35 kV. 6.35 kV will be the phase voltage. And obviously the thyristors will have to withstand the voltage which is peak of the voltage, because the voltage is Vm sin omega t, right? Vm sin omega t. So this is the voltage that the thyristors have to withstand. That they have to block. So what will be this is the RMS value. So what will be the peak value? 6.35 root 2. 6.35 root 2. That will be the peak value that TCR unit has to withstand. So this is 8.98. 8.98. Okay. kV. So so remember always that these voltages, they are line to line voltage and RMS values. Okay. The next question. Determine the value of the fundamental component of the TCR current. Okay. So here they have given this information, the firing angle and also the reactance. Okay. This reactance is the rated value. Okay. This is the rated value. That is the value of omega L, that is equal to 10, where omega is 2 pi multiplied by 50. Okay. So this is 10 ohm. This is the rated reactance value. Fine. Now the fundamental current we already saw when we were discussing ITCR fundamental, that we found out from the Fourier series. Okay, this is the fundamental. Fundamental. That's what you will have to find out. Okay. So what was that? That was minus Vm by omega L. Vm by omega L. Then 2 minus, think here we wrote the expression here. So this expression 2 minus 2 alpha by pi minus sine 2 alpha by pi. 2 minus 2 alpha by pi minus sine 2 alpha by pi. Right? So can any of you calculate and tell me the value? Yeah, please calculate this and tell me what will be the current value here. Here alpha is, the firing angle is 135 degree. 8.98 by 10 here. But remember, you will have to take all the angles in radian. Okay, here alpha and 2 alpha, you will have to they will have to be in radian, not in degree. Okay, so 2 minus two minus 1.5 minus so this is plus 0.318 0.318. Okay, just 0.318. So this becomes this into this is minus 0.7348 kilo ampere. Kilo ampere. So option B is the correct option. Then determine the conduction angle of the TCR. What is the conduction angle? Conduction angle is sigma and it is equal to 180 degree minus 2 alpha. Okay. How does this comes from? If you just see this diagram, okay. So we already saw that alpha varies from pi by 2 to pi. That is from 90 degree to 180 degree alpha varies. This is the range of alpha. When we are considering from the zero crossing of the voltage. But if you consider from the peak of the voltage, then the angle will vary from 0 to pi by 2. Okay. So it depends on from where you are counting the angle. If you are calculating it from zero crossing, then this varies from pi by 2 to pi. Okay. Now, if suppose this is alpha and this is the current, the conduction time duration is sigma and this duration is sigma by 2. Now, if you calculate here, you will see that this portion, this tiny portion here after pi by 2 plus this angle, this sigma by 2, okay, plus this sigma by 2, right? So this total corresponds to pi by 2 because why? Because the current peak will be lagging the voltage peak by pi by 2. So uh, alpha minus pi by 2 plus sigma by 2 plus sigma by 2 is equal to pi by 2. Okay. This is equal to pi by 2. Then what will be sigma? Sigma is pi sorry, I did some mistake. So So basically, this is we will derive it like this. Yeah. So this angle is alpha minus pi by 2 and then plus sigma by 2. Sigma will be pi minus 2 alpha. Okay. So sigma value is pi minus 2 alpha. So this is 135 degree. So its value will be 90 degree. Okay, there is a minus sign coming, but its value will be 90 degree. From this 0 crossing 1, the expression I was just deriving, from there you get an expression 2 pi minus 2 alpha. Okay, 2 pi minus 2 alpha that I was deriving alpha minus pi by 2, alpha minus pi by 2 plus sigma by 2. If you do like this, sigma by 2 equal to pi by 2 again. Okay. So in that case, you will get that. But anyway, this is the standard one, 120 degree minus 2 alpha. So the correct option is 90 degree. So these were the questions today. If you have any question, you can ask. Otherwise, I shall wrap up today's session and we shall meet in the next week. Okay.
Okay, ma'am. Thank you.
Okay. Okay, then bye. Thanks for attending the session.
Thank you, ma'am.